Okay, so so this is the first lecture on machine learning concepts, material, and this is really just a high-level overview of what is machine learning versus other stuff that you've seen in engineering or other fields. Okay, so let's first talk about what are the tasks we want to perform. So the ones I'll focus on for now are prediction, classification, and categorization. Prediction in statistics is called regression. So that's the term that has been adopted mainly in machine learning. But if you were just talking to your friend, you'd probably say, I want to predict this from that. Same thing with categorization. It's if you have a bunch of data and you want to make it into categories, invent some categories that neatly partition it. It's called clustering in machine learning, but you can also think about it as categorization. So let's talk about what these different things are. Let's start with prediction or regression. So it's just a simple example. Let's say that my goal is to use current and past data of some form to predict a future stock price. So here I have a plot, for example, of time and price of some stock. So, I want to know what is the price of that stock going to be tomorrow. So, what might some useful data be for making that prediction? Do you guys have some ideas? Yeah.
Like every single day's data of the stock price?
Yes, in the past, exactly. Today and past. Any other ideas? Did you have? Yeah.
The history of similar stocks to it?
Yeah, similar stocks. Any other ideas?
Sentiment analysis?
So what data would that describe?
Kind of like Twitter feeds and other
Okay, yeah.
environments.
Sure, Twitter feeds, news, all that stuff. Yeah.
Like how profitable the company is, maybe?
So yeah, other data about that company, some metrics, performance metrics. Sure, those are all great things. So that's exactly it. So it's like you collect a bunch of data, and maybe you stick all those data points together in some long vector, and maybe those data points themselves change every day. So you have today's version of the Twitter feeds and the profitability and the current stock price, and then you have yesterday's and so on. And using all that data, you want to predict forward, what is the stock price going to be tomorrow? So when you think about how would you go about this? So one approach, which we could call the kind of classic approach, maybe something that people would have tried 100 years ago, is to build some sort of mathematical model for how the stock price relates to all that other stuff. Now, obviously, that's really tough, right? If someone knew that model, they'd be very wealthy. And then the whole stock market would somehow change to counteract for that model, and then that model would no longer be valid. So it's not really feasible for a lot of problems to come up with a mathematical model. So that would be the classical approach. The machine learning approach would be to not use any model, but to try to learn a model just by looking at past examples of data, price, data, price, data, price, and to try to, just from the data alone, figure out the model, not from any economic theory or anything like that. Okay, so this is just one example. More generally, so one thing that's peculiar about this is we're trying to predict only one real number. More generally, you might try to predict a whole set of real numbers. Maybe you're trying to predict a whole image, which contains hundreds of thousands of pixels. So not trying to predict one thing, but many things. So in general, we would say prediction regression is estimating the value of one or more quantity given measurements of related data. It might be a time series, or it might not have anything to do with time. Just prediction. Hey, any questions on this task? Okay. Classification. So the main difference between prediction and classification is in classification, the thing we're trying to predict has a finite number of categories. And these categories, for example, let's say our objective is to recognize a handwritten digit from a little picture. So this is one picture, this is another picture, there's another picture, and so on. And in each of those pictures, you're trying to figure out what digit is being represented. Is it a 0, a 1, a 2, all the way to a 9? So it's a type of prediction in that you're given this little, collection of data, and you're trying to predict something about it, but you're not trying to predict a real number. You're trying to predict something between 0 and 9. And the main thing that's different is that real numbers are ordered, like, 0 is less than 0.1 is less than 0.2 and so on. But these digits, in some sense, yes, they're ordered, but in another sense, like, these are just shapes. I want to figure out, like, what shape is represented by this? What shape is represented by this? So in that sense, there's really no ordering between, different shapes. If that's confusing, let's say that instead of the digits, I wanted to have, like, my alphabet of possibilities was like 0, A, number sign, beta. Okay, so here you can see that there's really no clear ordering between those 4 things. They're just 4 different things. They're 4 categories. That's it. Okay, so that's the main difference between prediction and classification. Otherwise, they're very similar. You have a bunch of data, and you're trying to predict what is that data telling you about some quantity. Okay, and the main difference here is this is a category versus here it's a value, a real number. Okay. Okay, any questions about classification? Okay, so let's talk about another one, clustering. So in clustering, here's an example. Let's say someone gives you a big collection of text documents, and they say, well, I don't know, it's a whole bunch of stuff. Can you just, like, sort these into different categories? And so that's the task. You want to maybe figure out, oh, okay, all these documents here are about, maybe they're all like scientific articles. All these ones here are just news articles. All these ones here are short fictional stories, for example. Another example of this is, let's say instead of the data being text documents, the data are pairs of numbers x1, x2. So in that case, I can plot the data on this two-dimensional plane, and each of these dots here would be one data point, right? And so you're given this data set, which we're plotting here, and now you're asked, can you please sort those into categories? And the idea is that within a category, the things should be similar to each other and different than those in other categories. Right. So how would you do it in this case, just as a human?
Maybe 3 rough categories where you have the bottom left, and then your middle right, and then the bigger cluster in the other one.
Okay, sure, that's one. But yeah, or some people might say, well, actually, I think there are 2 here. So there's interesting about clustering is that there's many different ways to define the problem. So there's no correct answer. It really depends on how you define it. But I think you get the point of clustering. So what do you see as the primary difference between clustering and classification that we just talked about? So,
classification is trying to pin it down to one thing, or what was the thing before this called?
Yeah. Okay,
Yeah,
or
classification
prediction.
is trying to pin it down to one thing, and clustering is trying to find a series of things to locate a bunch of them together.
Okay, I would say actually that if you think about each data point here, the goal really is also to nail it down to one thing, which is the cluster index. So for example, if I decide to come up with 3 clusters, then what I want to do is for each of these points, I want to tell you which of the 3 clusters is part of. So in that sense, the target is the same. It's just one thing from a finite set, in this case, a set of 3. So what else is different, though, that's not about the quantity? The quantity we're trying to predict actually looks similar between classification and clustering, but there's something else that's very different.
I think
that the categories are decided before and then there's a predetermined categories, and this one you have to choose which categories as you go?
That's true. We're trying to define the categories, whereas in the other case, the categories are given. Anybody have a different way of expressing that? Yeah.
So with clustering, in a sense, I guess it's like a group of data that's been organized in a sense, but with the other one, it's like recognizing a data off of a certain database, as in like using a database of numbers that are handwritten, and it recognizes off that database.
Okay. So maybe I'll describe it in a different way. Let's think about the data that we're given for the problem. Like if we're given a lot of example data for each of these problems, what does that data look like? So in this case, I'm going to have, what's my example data?
They were discrete.
So, okay, so the targets are discrete. We'll call these things like y. So if I is going to index these different, this is like 1, 2, 3, 4, 5, all the way down here, then for this one, let's say we know that's a 0. So yi, or y0 would be 0, y1 would be 0, y3 would be 1, and so on. So those are discrete, but what else do we have in this problem as data? We don't have only the yi's. What else do we have? Have the images themselves, right? So we actually can think about the data here as like pairs of xi, yi. So for this particular data point, we have the image itself, which I'll string all the pixels together into a vector xi, and we have the label, which is yi. And then for this data point, we again have an xi and a yi and so on. And altogether, we have a set of these pairs where I goes from 1 to n being the total number of training examples. Okay, so this is called supervised learning because we have the data basically that we have tells us the relationship between xi and yi. And the task is given a new xi that I'll see later. I want to predict the y for that x. Now let's come over here. What's the data that we have in this case? Yeah.
Is it that we only have xi's?
Only have xi's, exactly. So our data is just xi's. We have no targets yi. So that we call this an unsupervised problem. It's just a bunch of xi's, and like someone said, we're actually trying to figure out what the labels are. It's like in some sense, we're trying to label this data. Okay, so those are 3 tasks, common tasks in machine learning. Those are not the only ones, but those are some of the main ones we're going to focus on this term. And now in terms of solving these tasks, as I mentioned before, traditional approach, something you'd use like 100 years ago, is to obtain a model from a scientific expert and then apply that model to the task. And in many cases, that's a really great way to go. Like, think about circuit design, right? Circuit design, the physics is, at least for most common circuits, the physics is pretty clear on how it works. Tried and true. If you want to design a circuit, well, we know how resistors work, how capacitors work, how inductors work. We know what happens when you put them together in a series and parallel, et cetera, et cetera. And we can use that scientific, expert knowledge to accomplish a task. But there's other approaches where that approach falls short. So as we saw with the stock market, in some cases we just don't have that scientific model. It's just not out there. But there's other cases where we actually do have a model, but somehow it's not convenient to apply it. So let me give you this example of acoustics. So acoustics is also pretty well understood in terms of the physics. Let's say the task is that maybe in this room, because of those hard walls, my voice is reverberating, and maybe someone in the back or something hears a lot of echo. They can't really hear what I'm saying. And so their task that they would like to perform is to do some sort of de-reverberation, echo cancellation, so they can hear me more clearly. And so if you knew about everything in the room, all the people in the room, all their absorption coefficients, all the geometry of the room and everything, you could apply those acoustical models and you could figure out based on that model exactly how to cancel that reverberation. But then if a bunch of people move, then actually the model has changed and you actually need a new model. And so this whole going to some equations and using those equations to solve noise cancellation, it just doesn't work, even though we know the physics. So there's just too many parameters that we need to learn in order to apply that model. Okay, so that's, when you think about this task is pretty well tackled by noise canceling headphones, right? And they actually do this. Maybe you don't often call it machine learning, but it's a kind of learning. It's adaptive filtering, which is also learning. It's basically they're listening to the environment in a clever way where they can basically figure out this is a signal, this is the reverb. We can subtract them in an efficient way to get rid of that reverb. And if the environment changes, like if someone walks in here, with a blaring boombox, then the headphones would adjust to that. They learn on the fly and they adjust. So that's an example of learning. So in machine learning, what we do is we build a model based on many examples of data. The data could be something we collected, or like in the headphones case, could be something that's streaming at us. But we essentially learn that model rather than consulting an expert. And then that allows us to do, in many cases, solve problems that you couldn't otherwise solve. Okay, any questions on this? Okay. So in order to do this, I'll get into a little bit of details here, and it's okay if you feel lost, because really this is the stuff we'll get through as the term goes on. So at the end of the term, hopefully you will understand all this. It's okay if you don't right now. But basically, there's a few key ingredients to do this machine learning stuff that I just talked about. And we need a way to describe it using math. So the first thing we need is a modeling function. This is going to be the thing that does the hard work, like the prediction that we saw for stock market. So this modeling function, it's going to take in a quantity, like it's going to take in all our data about the stock today and previous days, and it's going to output the value of the stock price tomorrow. But it's a function that has a lot of adjustable parameters, a lot of knobs that can be wiggled. And our job is really to just adjust all those parameters so that this thing is doing a really good job of prediction. Okay, so those parameters, we're going to call them theta. And all throughout the term, we're going to consider that there's d of them. D is going to be the number of parameters that we're trying to adjust. Okay, and so this f sub theta means that f depends on theta, but this is the input here, and then it has some output. Now, in order to train this model to adjust those coefficients theta, we need to have a function that tells us whether it's doing well or poorly, and this is what we call the loss function. So the loss function is going to take in often a pair of things and basically tell us, okay, here's the truth, here's the prediction, and if they're similar, the loss is going to be small. If they're very different, the loss is going to be large. But there's many different ways to define that loss. I'll give you an example on the next page. It really depends on the task you're performing, which is the right way to define it. Now, in order to do all this training, we need a training data set. So for like the supervised problems, we talked about pairs of xi and yi. So lots of xi, yi pairs. And that data set and our model together, we're gonna use to evaluate the loss and say, okay, on our data, are we getting large loss or small loss? If we're getting large loss, can I somehow adjust the parameters theta to make the loss smaller? In other words, to get the performance better? So doing that is our goal, but that's often tricky. You might have like millions of parameters. How do you do that? So for that, we need some sort of optimization algorithm. So the goal of that is to find the parameters that yield a low loss on the training data set. So that's kind of putting things together. Any questions on this so far? Okay, so let's go a little bit deeper, a little bit more math. And this is back to the stock market prediction example. So let's say that we are trying to predict this future stock price Y, and this is just a real number. And our currently available data, which we've collected today and all in the past, we're going to stick all that stuff into this vector x. And here you can see x is going to have d different entries. So all throughout this course, I use boldface notation for vectors and matrices, and I use non-boldface notation for scalar quantities, because that's often helpful to figure out, like, is this thing I'm dealing with a vector, or is it just a single scalar? Okay, so so this function function f theta, it's going to take in x, and our goal is that it outputs an accurate estimate of y. And how are we going to build that? Well, today, the common way to build that is to use a deep neural network. And theta would be all the different weights of that deep neural network. Those are the things we want to adjust. We're going to talk about these things later. It's not important if you don't know what that means right now. Okay, so now we have to define a loss function that makes sense in the context of stock market prediction. So this loss function is going to look at two things. The predicted y, we'll call it y hat, is the prediction, and the true y. And if these things are very different, it means we have a bad prediction. If these things are very similar, good prediction. So we just now need a loss that measures the difference, how different are these things, are these two quantities. So there's still some freedom there. One very common way to do this is quadratic loss. You look at this squared difference, but there's other options. You can look at like the absolute difference, and they actually behave a bit differently. Absolute difference is going to work better when there's outliers in your data, which are like kind of weird values that don't really fit the general pattern. So there's times when you want to use this one. There's other times when you want to use this one. In any case, we have to make a choice there. And finally, we need a data set that contains many past examples of those x and y quantities. And putting everything together now in an equation, we get this. So let's look at this slowly. So this is my prediction model. Here I'm putting in the ith training example. The ith, we call this the feature vector. And this is going to output its prediction of yi. Yi without the hat would be, this is the true, this is, according to the data, this is the true yi for that xi. And when I put xi through the model, I get something a little different, which is the y hat. And now I plug those into my cost j that tells me how different are they? How bad is this approximation? And now I'm going to average that over all my data samples. I have a data set here of n different examples. So this is my average loss on my whole data set with the loss I chose, with the model I chose. And somehow I want to adjust these parameters theta to minimize that loss. And so we express that using argmin. Okay, so does anybody know what the difference between min and argmin is?
Inverse.
Not exactly. I don't know. Maybe I'm misunderstanding. Okay, so if we didn't have the arg here, what this means this means that's the smallest value of this quantity that you can ever find by adjusting theta, right? So that's like the smallest average loss. But what we actually wanted is not the smallest average loss. We want to know the weights theta that cause that smallest average loss. So the arg says it's like the minimizer, not the minimum, but the minimizer, the theta that yield the smallest. So that's what minimizer. That's what the arg is doing for us. And so finally, at the end of the day, this theta hat, this is like saying these are the best parameters, the best weights in my neural network in terms of predicting the training data, the training y from the training xi. Given that particular architecture of the neural network, maybe it's a weak network, so even if I optimally choose theta, it's still not very good. That can be the case. But that's essentially what we want to do. And in order to solve this math problem, we need some algorithms to do this. This is a non-trivial task, so we're going to learn about that. But once we know those theta hats, those are the weights that supposedly give a good prediction, we plug those into the model, and we get f theta hat. And now we apply this in the real world. Someone gives us new stock data about some new stock or maybe tomorrow's stock, and we want to predict the next day's stock price. So we apply that model once it's trained. Okay, question?
What was the theta here again?
Theta are all the parameters of our model. So if my model is a neural network, then there's all the adjustable weights in the neural network. Sometimes it's going to be, when we start, it's going to be much simpler. It's just going to be, I'm going to take a linear summation of all the data that I have, the x's. I'm just going to sum them together with some scaling. And so the theta is just going to be like, what are the scaling coefficients?
Okay. So like the f of theta or f sub theta, that's like the function of my thetas with the inputs.
So
of
I'll give you an example. So example, y hat I is some function of theta xi. And in this case, what I'm saying is it could be like theta is a vector. It could be like theta 1. Okay, so I have to be a little careful here. Let me do it without the i's. Sorry. Okay, so this x is going to be a vector, and let's just say for simplicity, I only have two values in my data, x1 and x2. These are two scalar numbers, and I'm using those to predict y. And so the simplest predictor that I can come up with is just some scaling of x1 plus some scaling of x2. And so now I have two adjustable parameters, theta 1 and theta 2, and I need to adjust those so that the y hats I get are as close as possible to the true y hat, according to my training data examples. Okay. All right. Good questions. Are there any other questions? Yes.
How do you know which loss function to use?
That's a great question. That's one of the things we're going to talk about a lot in this term. There's no easy answer to that question. Yeah.
Just to clarify this example, we don't know the parameters that are ideal to minimize the loss function, so we're testing different thetas.
We're gonna come up with some algorithms that will figure those out. In some cases, we'll be able to write an equation directly that tells us what they are. But in more complicated cases, there's no equation. We can't do it in closed form analytically. So we're going to come up with an algorithm to do it. That's what usually happens in practical machine learning. Okay. Any other questions? Yes.
Are loss functions strictly scalar valued functions, or could they also be vector valued?
They're going to be scalar valued. Sometimes the loss function could be a sum of different losses, but at the end of the day, they all need to be summed together so you get a single, judgment of is this good or bad. Yeah. Okay. Great. Okay. So that's the intro, and then today I don't have that much time for questions. I'll have a lot more time for questions on Friday. But if you have a quick question, I can handle it after class. But if it's just like a long discussion, maybe we can postpone it to Friday. All right. See you guys on Friday.